This is going to be a short video about Chapter 15, which deals with fluids. Okay, so first we're going to talk about density. And density is mass per unit volume. And the symbol that we're going to use for density is this Greek letter rho. It looks kind of like a P. And rho equals mass divided by volume. And for the SI unit, we're going to use masses in kilograms, and volumes are going to be in meters cubed. So the unit would be kilogram per meter cubed. And this table is from your book. It lists the densities of various materials. And I would like to point out water on here, because you're going to see that given in some of your problems. So for fresh water, that density would be 1,000 kilograms per meter cubed. And they won't necessarily always tell you that in the problem. The other thing we're going to talk about is pressure, and pressure is force per unit area. And the symbol that we're going to use for pressure is a capital P, and P is equal to F divided by A, or force divided by area. Forces are going to be in newtons, and areas are going to be in meters squared. So that is Newton per meter squared. And pressure, the same force that's applied over a small area, results in a greater pressure. So if you think about poking it with your finger or versus a pin, since this has a much smaller area, it's going to be a much larger pressure. Here I have an example. It's dealing with finding pressures. And we want to find the pressure exerted by the tip of a crutch on the floor. So I'm going to find my pressure. I'm going to have to take my force divided by the area. And the force is going to be this person, and F equals M times A, which is going to be my 9.8, or in other words, weight is equal to mg. Then I'm going to be dividing by my area, and since this is a circle, my area is going to be pi times r squared, and this centimeters is going to have to be in meters, so 0.025 squared, pi r squared. If I multiply the top, I get 637. And on the bottom, I'm going to get 0.00196. And if I divide those, I'm going to get a pressure of 3.2 times 10 to the 5th Newton per meter squared. And that's going to be the pressure that's exerted. And this is used in your assignment on 15.8. Okay, the next thing we're going to talk about is atmospheric pressure. And atmospheric pressure is pressure that we have due to the weight of the atmosphere above us. And atmospheric pressure is pressure, and then it uses this little subscript AT for atmospheric pressure. And our atmospheric pressure is 1.01 times 10 to the 5th Newton per meter squared. And that's the SI unit, Newton per meter squared. And in case you want to know, a Newton per meter squared is the same thing as a Pascal. So this could be 1.01 times 10 to the 5th pascals. And the answer that I just got in the last problem, 3.2 times 10 to the 4th, this could also be pascals, because a Pascal is the same thing as a Newton per meter squared. Okay, other units, so this could be in kilopascals, or pounds per square inch if we're using that, or bars. Most of the time we're going to be dealing with pascals. Gauge pressure is slightly different. Gauge pressure is what a pressure gauge would read, and that tells me how much more pressure there is in the object than in the atmosphere around it. So to find gauge pressure, I take the pressure of the object and I subtract atmospheric pressure. So it's just telling me how much more there is in the object than in the atmosphere. And when we think about gauge pressure would be like what you were reading in your tires. Okay, pressure in fluids depends on the depth that you go. The more depth, there's going to be more fluid up above pushing on it. So as the depth gets larger and larger, there's going to be more pressure. So in this case, we have force on the top. That's going to be atmospheric pressure times the area. And at the bottom, we're going to have that atmospheric pressure plus we're going to have pressure from the fluid up above it. And this is rho, which is density, times g, which is 9.8, and then times your depth or your height. And this atmospheric pressure is that 1.01 times 10 to the fifth. Okay, so if we have a pressure here, the pressure down here will be larger because it will be this pressure that I had here plus the pressure from the depth. In this case, I have an example, and it says the water in a lake behind the Hoover Dam is 221 meters deep. What is the water pressure at the base of the dam? So if I want to find the pressure, this is going to be the atmospheric pressure plus the pressure of the depth, which is that rho GH. Our atmospheric pressure, we said, was 1.01 times 10 to the fifth pascals, plus rho, and I said this was one of those on that chart that you were going to need. The density for fresh water is 1,000 kilograms per meter cubed. G is going to be 9.8, and my height is 221 meters. So the total pressure that I get, this would be the atmospheric the pressure here from the depth, and if I add those up, I should get a pressure of 2.27 times 10 to the sixth pascals. And you are going to have one like that in 15.20. It's asking you to find the pressure at a certain depth. Okay, a barometer measures atmospheric pressure and fluid pressure, and the barometer is usually in mercury filled up here. There's like a mercury vessel, and then the mercury pushes up. Because I have atmospheric pressure that pushes down on this pool of mercury, the mercury then pushes up in the tube. And then there's a scale over here that's in millimeters or inches, and that's how we get millimeters of mercury or inches of mercury, which would be how we measure atmospheric pressure. And 1 atmosphere of pressure is 760 millimeters of mercury. And on the news, you'll find it measured in inches because they use inches instead of millimeters. And in a barometer, the mercury will rise until the pressure in the fluid is equal to the atmospheric pressure. And in a container where the fluid can flow freely, the pressure will be the same throughout. And the pressure is only going to be related to the depth. Pascal says that the pressure is transmitted unchanged through every point, which means the pressure here is going to be the same as the pressure over here, but the areas are different, which leads to an application in hydraulics. So if we have the pressure on this cylinder equal to this other cylinder, then the force divided by the area of one cylinder would be equal to the force divided by the area in the other cylinder. Since this has a large area, that means there can be a large force. Over here, if the area is smaller, it's going to take a smaller force. So a small force could lift a huge car. Okay, Archimedes deals with buoyancy. And the buoyant force is the upward force from the fluid. In other words, when you get in the water, you're feeling this buoyant force that pushes you up. And this is because there's increased pressure at the bottom. So in this case, I have a block, and this is going to be the pressure of the fluid on it from the sides, because that pressure is going to be all the way around. And then we're going to have pressure here from the fluid and the pressure here from the fluid. So we can see between these two, since there is more pressure on the bottom than there is at the top, we get this net force upward. And to find the buoyant force, I take the density, which is rho, times g, times the volume. And since this is a force, the unit is going to be in newtons. Okay, Archimedes says that an object that's completely immersed or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid that's displaced. In other words, the buoyant force is equal to the weight of the fluid that's displaced. And by the weight, that could be air and water, or water, whatever it is. And an object floats when it displaces an amount of fluid equal to its weight. So when those two are equal, then it's going to float. Because then we're saying that this is my object. Here's the buoyant force. And here's the weight. And when those two are equal, there's no net force. So it's going to float. So if an object is made of a material that is denser than water, it will only float if it has pockets of air or something that's going to make its density less than water. So in order to float, the density of the object has to be less than water. If it's greater than, it will sink. And how well an object floats depends on the density of the object and the fluid. So we can see here that if we have the volumes, a ratio of the volumes, that's the same thing as a ratio of the densities. So the volume for a submerged object is going to be equal to the volume of that solid, the density of that solid, and the density of that fluid. So if I take a ratio of the density of that object compared to the density of the fluid, that's going to be the same as the volume that's submerged over the volume of the object. Our buoyant forces, we're going to have one that's talking about a block. We're going to have to be trying to figure out how well things floats. You also have a tutorial that's on Archimedes. And also number 15.33 is going to be dealing with buoyant forces and Archimedes. And this particular picture with the forces all being pushed on it, there is a problem about goldfish on your assignment, where you have to draw the forces that are present on the goldfish. Work is done. Okay, so this example kind of goes back to our buoyant force. And it says we have a balloon that's filled with helium at a certain density, and the balloon has a certain radius, and they want to know the maximum amount of weight that it can lift. So if this is my balloon, then I know that I'm going to have a buoyant force up, and I'm also going to have a weight of my object that is down. And if I want to find the buoyant force of my object, the buoyant force is going to be equal to rho times G times V. Okay, so my density is 0.179, G is 9.8, and then I'm going to have to find my volume, and this is going to be the volume of a sphere, which is 4/3 pi r cubed. 4/3 times pi times 4.9 cubed. So if I take 4.9 cubed and I take it times pi and times 4/3, I get 492.8 meters cubed. Okay, so I'm going to go ahead and find my buoyant force by multiplying all those together. And I get 864 newtons. Now, my weight is going to be the weight of the balloon, which is down. And my weight is going to be equal to m times g. So 32 times 3.2 times 9.8, which is going to be 31.36. Okay, so the maximum weight that this can lift is this whole amount, but this weight is going to be subtracted from that because I already have a weight down. So if I take 864 minus my 31.36, that's going to tell me the maximum amount of weight that it can lift, because part of this weight is being taken up by the balloon. So if I subtract those, I'm going to get 830 newtons. Says that the volume of fluid per second in a tube is the same at every point. So if the pipe is narrower, the flow is faster. Alright, so going onward with our continuity, we said that if this area gets smaller, then the velocity increases. And our continuity equation says that rho 1, meaning density times A1 times V1, is equal to the density times A2 times V2. And most of the time that's going to be the same density, because although gases can be compressed, most liquids are not. So that means we could cross out those densities and we are just left with A1 V1 equals A2 V2, where this is area, this is velocity, this is the area and the velocity for the second one. Okay, and when a fluid moves from a wider area of a pipe to a narrower one, we said that the speed increases and work has been done on it. And if I wanted to find the amount of work that was done, it would be a difference in the two pressures multiplied by the change in volume. This gives rise to Bernoulli's. Bernoulli's is basically conservation of energy in a fluid. So this is going to be my pressure. This is going to be like my kinetic energy, 1/2 rho V1 squared, where this is, think about kinetic energy. This is going to be potential energy because this is due to having a height. And this is how we found the pressure and the depth of a fluid. So we have those three terms. Basically, we're going to be exchanging pressure potential energy, kinetic energy, and potential energy, gravitational potential energy. So this is on one side, and this would be on your other scenario. And it's conservation of energy, which means that if the height doesn't change, then that means you can cross out those terms because gravitational potential energy is not going to be a factor. If your speed is not changing, then I can leave out the kinetic energy term because it's not going to be a factor. So this is the full-blown equation, and I only have to use certain parts of it depending on my problem. So here's an example. This is going to use not only the continuity equation, but also Bernoulli's. And that problem that I mentioned earlier, the 15.60, this is going to be using both parts, just like this example. So it says that the buildup of plaque in the arteries can decrease the diameter from 1.1 to 0.75 centimeters. And the speed of the blood flow was 15 centimeters per second before of the buildup. And they want me to find the speed and the pressure in the region of plaque buildup. So I first am going to use my continuity equation. Okay, area. These are circles, so this is going to be pi r squared v1 pi r squared v2. Okay, so I started out with a diameter of 1.1, so I'm going to have to divide that in half in order to get my radius, and then I'm going to change it into meters. And it said that my velocity was 15 centimeters, so this is 0.15 meters. And then I'm going to do pi. Now I change it to 0.75, so I'm going to have to change that into meters and divide it in half to get my radius. My pi's can cancel. And my new velocity is going to be 32 centimeters per second. I get 0.32 meters per second. I just changed that to centimeters per second. And we can see that that sped up. The velocity gets bigger when the diameter got smaller. Now the second part of this, I have to find the pressure. And I didn't have an original pressure, so I'm going to have to find the pressure drop. So I have the P1 plus rho GH plus 1/2 rho V1 squared equals P2 plus rho GH plus 1/2 rho V2 squared. Alright, and in this particular case, I don't have any difference in heights, so I don't have to use those terms. And I'm looking for the difference in the pressures. So I'm going to take P1 minus P2, and moving that over the other side. Now, if I had a pressure originally, I would just plug it in here, and then I could find the pressure at the second case. But they didn't give me the pressure. I'm just going to have to find the pressure drop. So I'm going to be taking the 1/2 rho V2 squared minus 1/2 rho V1 squared to get the difference in my pressures. So 1/2, and I'm going to assume that in our blood that it's mostly water, so I'm going to use the density of water. And V2 is my 32 centimeters per second that I got to square. 1/2, 1,000, and this is going to be my other one, which was 15 centimeters per second. I'm going to go ahead and leave those. I'm going to change those from centimeters to meters. So I think I'm going to go with 0.15. And here I'll go with the 0.32. So P1 minus P2, the difference of 41 pascals. Difference in their pressures. Okay, Bernoulli is easy to demonstrate, and there's going to be a tutorial, a Bernoulli's tutorial, about blowing between balls, which is very similar to the idea here. Applications. Low pressure at high speeds is what rips roofs off of houses in hurricanes and tornadoes, because we have low pressure. In other words, if we think about our house, we're going to have high speed here, and we're going to have low speed through the house. So that's going to create low pressure here and high pressure here and lower pressure here, and the high is going to push on the low, and that's going to cause the roof to be lifted up. And that's why a lot of times you're going to have a vent in your home in order to try to equalize those pressures. It's the same thing that happens with an airplane wing when we look at lift. So we're going to have the speed of the air over the wing and the speed under the wing. And the speed over the wing is going to be much faster, therefore this is going to be lower pressure, and this is going to be higher pressure. And the high is going to push up on that low, and that's what's going to be causing the lift in my airplane. And we can see here we have a side of our container, and we have a hole that was in that container. And both the outside and the top, both the top and here, are exposed to atmospheric pressure. So in this case, since I have a greater depth here, then in that case it's going to have a larger velocity when it enters or exits. And if the fluid is directed upwards instead, it's going to reach the height of the level of the surface, because here the amount of energy that I have here has to be equal to the amount of energy that I have here. And since I'm exchanging kinetic energy for gravitational potential energy, it can only reach the same height that I started. Viscosity, there's not going to be really any problems dealing with viscosity, but viscosity is a form of friction that's felt by fluids as they flow along surfaces. And in this case, we can see that there's going to be some friction with the sides of the container. So the velocity of the particles on closer to the end where they're having friction is smaller than through the middle. So the maximum velocity is going to be here in the very center. And in a fluid, then we have forces in a drop keep the surface area at a minimum. In other words, it tries to keep this thing pulled together. And in small objects, like insects and needles or whatever, they can stand on top of water, even though they're too dense to float because of the surface tension of the water. Alright, so those are some equations that we were using. Notably, we used this one, and we were using this one, and we used that one as well. I didn't have an example where I used that one. We did use the continuity equation, and we just used this A1, B1 part. because our densities, well, A1V1 equals A2V2 because our densities were staying the same. And we need an example here. There is going to be one on your assignment where you're going to use the escape velocity coming out of the side of the hole, and this is 15.64.